Good evening. My name is Wick Haxton. I'm up here because I'm the new chair of the physics department, so it's my honor to greet you. This is the, thank you. This is the 31st annual Emilio Segrè lecture. It's actually made possible by the Raymond and Beverly Sackler Foundation, who've supported it over many years, so we want to thank them. It's brought to us a really remarkable set of speakers over the years. I could just mention a few of them, but they include Hans Bethe, Masatoshi Koshiba, Bert Richter, Mildred Dresselhaus. Last year, Ray Weiss, who won this year's Nobel Prize for the discovery of gravitational waves, and Bob Bergeneau, our former chancellor. I thought I should tell you a little bit about Emilio. We're very proud of him. He was one of the really distinguished experimentalists in our department. He was born in Tivoli, Italy in January 1905. His father was an industrialist, and Emilio described his extended family as intellectuals, academics, lawyers, and engineers. The family moved to Rome in 1917. Emilio completed high school there, and then he entered engineering school at the University of Rome. He soon switched to physics, where his friends included Ettore Majorana, Edoardo Amaldi, and Franco Rossetti. He was tutored by Rossetti in experiment and by Enrico Fermi in theory, and the whole group was the oversight of the whole group was provided by the Institute's director, Corbino, and so they were called Corbino's boys. Segrè received his doctorate under Fermi in July 1928, then spent most of 2 years in the military. He returned to the Institute in 1930 as Corbino's assistant. Already at that time, he did important work on his own on the Zeeman effect in alkali atoms. He identified forbidden lines that had been not understood as quadrupole transitions in these atoms. Segrè then moved to Amsterdam to work in Zeeman's laboratory, and later on he moved to Hamburg to join another famous physicist, Otto Stern. In 1933, led by Fermi, Corbino's boys turned to a new field, from atomic physics to nuclear physics. It was stimulated by Rutherford's work, and they learned radiochemistry, how to synthesize radioactive elements by neutron bombardment. In 1935, Segrè became professor of physics at Palermo. The next year, he married Elfrida Spiro, and in the following year, Claudio, the first of their 3 children, was born. Shortly after they married, the couple made their first visit to the US, and they stopped at Berkeley's radiation laboratory. Lawrence allowed Segrè to take pieces of his cyclotron, which had been radiated, back to Palermo. With his colleague in Palermo, Carlo Perrier, Segrè succeeded in extracting from the metal the element technetium. It's a remarkable element that has no stable isotopes. So this is the first example of isolating what should be considered an artificial element. 15 years later, technetium became very important in astrophysics. It was discovered in the atmospheres of certain stars, and that proved that these stars were continually synthesizing heavy elements by some mechanism. In the summer of 1938, Segrè returned alone to Berkeley to continue his work. While he was here, Mussolini's government passed laws that barred Segrè and other Jews from universities. Lawrence, in response, hired Segrè as a research associate, and Segrè brought his wife and young son to Berkeley. With the war depleting the Berkeley faculty ranks, Segrè became a lecturer in Berkeley physics in the department in 1941. In 1943, he accepted Oppenheimer's invitation to join the Manhattan Project at Los Alamos, where he headed a group that was measuring fission rates in plutonium and uranium. He returned to Berkeley as a full professor in 1946, so a quick promotion, setting up a research group to study nucleon-nucleon scattering with neutron and proton beams that were provided at the lab, with increasing energy as the radiation lab became more skilled in building more powerful cyclotrons. In 1955, Lawrence and colleagues designed the Bevatron. We could produce 6 GeV protons, and that energy was sufficient so that when the protons hit a stable target, you could produce a proton and an antiproton. So a search started to find the antiproton, and later that year, Its discovery was announced in a paper by Chamberlain, Segrè, Wineland, and Oscillations. Chamberlain and Segrè were awarded the Nobel Prize for this discovery in 1959. After the prize, Segrè continued to oversee research, but also took on other responsibilities at Berkeley. He taught undergraduate quantum mechanics and nuclear physics, and he became interested in the history of science, an interest that he continued after his retirement in 1972, continuing to teach. On campus, he served on the university's Crucial Budget Committee for 4 years and then became physics department chair for a period. Over his 5-decade association with Berkeley, he helped train 30 PhD students, among them C.S. Wu, Herb York, Tom Ypsilantis, and Herb Steiner. Emilio died from a heart attack at the age of 84. He was walking near his home in Lafayette when that happened. So there are many friends of the physics department that are here tonight, so I want to say a few words. We're very proud of the fact that Berkeley is a first-rate physics department. And our donors help us by supporting the physics that we do and also to train students that we hope can follow in Emilio's footsteps. Berkeley is really special. It's a public university that competes with the best in the world. We consider Harvard, MIT, Stanford, and Chicago as our peers. In fact, in the last ranking of world universities, we were second in physics behind MIT, and Berkeley overall was first in the natural sciences. But in a sense, we're more than that, because as part of California's remarkable system of higher education, we represent opportunity. In this year's New York Times College Access Index, this is a measure of how well an institution is doing to advance the American dream. 6 of the top 10 places were taken by UC campuses, which is really remarkable. So our system is really helping address one of society's important problems right now, important challenges, the growing gap between the rich and the poor. We think it's important for Berkeley to continue in this role despite state support that has dropped rather dramatically over the past 15 years. Private support has helped us actually fill much of that gap. This semester, for example, the first 100 students are enrolled in our new state-of-the-art Physics 5 laboratory course. This is a course designed to teach beginning physics majors, experimental physics. So this would really have pleased Emilio. Donations provided by some members of this audience provided the bulk of the support for this construction. We also created a new course to help transfer students continue their education at Berkeley. The community colleges in California remain an important and affordable doorway into UC, and Physics 198 is designed to help our transfer students get through that doorway successfully. We're also working with the industry community here in the Bay Area. Industry friends are partnering with us through a new program called BP2. They recognize our critical role in producing technically literate students that they need to keep our high-tech economy moving forward. So that's the end of my commercial. Now it's my great pleasure to introduce one of our department's most valued members, Professor Hitoshi Murayama. Hitoshi is the McAdams Professor of Physics at UC Berkeley. He's also director of the Kavli Institute for the Physics and Mathematics of the Universe, located at the University of Tokyo. So his Pacific Rim wave function makes him uniquely qualified to introduce tonight's distinguished lecturer.
Thank you, Wick. So this is my distinct pleasure to introduce the Professor Takaaki Kajita to you tonight. As part of a little formal introduction, so Dr. Takaaki Kajita is a special university professor at the University of Tokyo and also director of the Institute for Cosmic Ray Research at the University of Tokyo as well. He received his PhD from the University of Tokyo School of Science in 1986 and has been doing research once he got into the PhD program at the University of Tokyo, and then continued to do research under the direction of Professor Koshiba, who was also a Nobel laureate back in 2002 for discovering neutrinos that came from a supernova explosion in a different galaxy. So there's a very long tradition of studying neutrino physics in Japan in underground experiments. So the experiments that he worked on, the formerly is a Kamiokande experiment, where Koshiba got Nobel Prize for, and more recently, Super-Kamiokande Detector, which is much bigger, at the Kamioka Observatory in central Japan, deep in Japanese Alps. And there, he actually discovered evidence for a phenomenon called neutrino oscillation, which you're going to hear more about later, which also points to the fact that neutrinos, which used to be believed as in exactly massless particles like photon, actually do have tiny but finite mass. And among all the Nobel Prizes that have been awarded to physics, this is the first Nobel Prize that was awarded to an evidence that so-called standard model of particle physics is not complete. There's more to it. But we haven't understood what exactly that is. So this really opened a new window beyond the physics of the standard model. And I was there when he presented this result at a Neutrino International Conference held in Takayama in Gifu Prefecture in Japan back in 1998. And after he showed, in old days, in 1998, it was not computers monitor like this one. He used this transparency one by one. And as he progressed, it became very clear that this was really a leading to the major discovery of this first evidence of physics beyond the standard model. At the end of this presentation, I was sitting in the audience, and I stood up. And I realized that many others around me also stood up and gave him standing ovation. It was that historic moment. I was really moved back then. And as I mentioned already, he won a Nobel Prize in Physics in 2015 for this major discovery. And I also got to know him very well. As the data was getting more and more mature, I communicated with him a lot about what these data actually meant. And I also suggested a different kind of analyzing the data. I did my reanalysis myself. I also eventually got into other neutron experiments myself. So I got to know him extremely well. And one thing I cannot overemphasize before bringing him up on stage is that for a Nobel laureate, he is a really nice person. You're going to see that. Okay, so please join me in welcoming Dr. Kajita, Takaaki Kajita on stage.
Thank you very much for the very kind introduction. Also, I want to thank the UC Berkeley people for the invitation to the Segrè lecture. This is really a great honor for me. And today, I want to talk about neutrino oscillations at the Super-Kamiokande detector. Well, you see in this page, you see something behind the title, and this is the Super-Kamiokande experiment. And I have been doing the experiment, researches with this detector. This is the outline of this talk. First, I want to have a brief introduction on neutrinos. I assume many of you know neutrinos, but maybe some of you have no idea about neutrinos. Therefore, I want to have some slides on neutrinos. And then I want to begin this talk with the Kamiokande experiment. That is the experiment before the Super-Kamiokande experiment. Then I want to introduce Super-Kamiokande detector, discovery of oscillations. And well, since the title of this talk is Oscillations, Neutrino Oscillations with Super-Kamiokande, therefore I want to talk about various neutrino oscillation studies with Super-Kamiokande. And before finishing, I want to talk about the possible future neutrino oscillation experiments. Okay, what are neutrinos? Well, this is the short introduction. Neutrinos are fundamental particles like electrons and quarks. Neutrinos are, say, something like electrons without electric charge. And well, actually, this has a significant consequence. Neutrinos can easily pass through even the Earth. Now, well, this is another page. Well, in addition, I want to say that neutrinos have three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And neutrinos can, well, although I said neutrinos can easily penetrate through the Earth, but neutrinos can interact with matter very rarely. And a muon neutrino produces a muon, and the electron neutrino produces an electron. Therefore, if we observe a muon, that means here a muon neutrino came. So that way, we know the neutrino type. And finally, I want to say that in the very successful standard model of particle physics, neutrinos are assumed to have no mass. And of course, well, we are physicists, and therefore we have been asking neutrinos really have no mass. Okay, that is the end of the introduction on neutrinos. Now I want to move on to the Kamiokande experiment. Well, the story began about 40 years ago. In the 1970s, new theories that unify strong, weak, and electromagnetic forces were proposed. Well, this was a very attractive theory, and we wanted to confirm or at least check if these theories are correct. And these theories predicted that protons and neutrons should decay with the lifetime of about 10 to 30 years. Well, of course, 10 to 30 years is a long lifetime. And, well, we don't care about the lifetime proton in our daily life, but this number seems to be very important. Therefore, several proton decay experiments began in the early 1980s, and one of them was the Kamiokande experiment. And you can see the sketch of the Kamiokande detector. It is a 3-kiloton water Cherenkov detector. Well, Kamiokande has a tank of diameter of about 60 meters and the height of also 60 meters. And as you can see, inside the tank, photodetectors were installed, and these photodetectors detect the Cherenkov light that was produced by relativistic charged particles. And that way, by detecting photons, we knew that charged particles propagate in the water. Now, maybe some of you have no idea where is the experiment. And, well, this is the location of the experiment. Well, of course, with this map, you do not have clear idea where is this location. So I show you a photo. Now, this place is like this. And, well, you can see mountain. And in fact, under this mountain, the Kamiokande detector was located. But also you see that there seems to be no human activity. That place would be not easy to do experiment. But fortunately, well, there are some human activity there, and therefore we were able to do the experiment there. In fact, there was a mining activity, and we used the mine to locate the Kamiokande experiment. Now, in the spring of 1983, we constructed the Kamiokande detector. And this photo was taken in the morning of the spring of 1983. Well, with this number of people, essentially we constructed this 3-kiloton water experiment. And, well, you can see Professor Koshiba in the middle. He was my supervisor, and also, as introduced, he was the Nobel laureate. He received the prize in 2002. And well, you can see maybe 2 meters behind him, there are 4 young students. And well, they were the people who worked in underground for several months. Anyway, well, every morning we took a train, mine train, starting at 7:10, and took a 3-kilometer mine train ride, and then went to the underground site. And in the underground, well, we constructed the Kamiokande experiment. And this photo was again taken in the spring of 1983. And well, we installed the photodetectors onto the detector wall. And for this, we decided to use, as you can see, both. Well, initially, we discussed how we should install the photodetectors onto the detector wall. And initially, we thought maybe we could use some catwalks and so on. But well, we are not an expert at working in high place. Therefore, we decided to use the rubber boats. Of course, the working conditions were not so great. But well, we thought it's much better than falling from the 15-meter high. Anyway, we worked hard for several months. And in July 1983, the Kamiokande experiment began. And well, we started the search for proton decays. But unfortunately, although we worked hard to search for proton decays, we were unable to find any evidence for proton decays. Instead, we observed, well, tens or maybe, well, several tens of atmospheric neutrino interactions. Well, these neutrinos are produced by cosmic ray interactions in the air. And these, well, neutrinos come into the, well, of course, most of them pass through the detector and pass through the Earth and go to the space. But some of them interact in the Kamiokande detector, and they are the most serious background for proton decays. Therefore, well, we increased the statistics of these background neutrino interactions. Anyway, experiment began in 1983, and I received my PhD in 1986 in a search for proton decays in Kamiokande. As I said, we had no evidence for proton decays. But anyway, at that time, I was still hoping to improve the proton decay analysis and find the proton decay signal. Therefore, soon after getting my PhD, I began to improve the analysis software in order to, of course, improve the proton decay searches. And one of the software was to identify the particle type for a Cherenkov ring. Namely, I wanted to know if a Cherenkov ring is produced by an electron or by a muon. Okay, actually, this one, the upper one is a Cherenkov-like pattern produced by an electron, and the lower one was produced by a muon. Anyway, since we have developed the new software, we have to check if the software functions properly. Therefore, as a test, the neutrino flavor was studied for the atmospheric neutrino events. Then, surprisingly, it was found that the number of muon neutrino events was much fewer than expected. And well, of course, this implied that we made some mistake in the new software development. Because, well, of course, we are in the middle of the development, and the result was strange. That means the software was wrong. Anyway, so we thought that there must be some mistake in the software, or maybe some other place. But anyway, there must be something wrong there. So we started various studies to find mistakes. That was just at the end of 1986. Well, we worked hard, and actually we worked for about a year to find out what was the mistake. But we were unable to find any serious mistake in the analysis or even in the simulation. So we concluded that muon neutrino deficit cannot be due to any major problem in the data analysis nor the simulation. And therefore, well, at that stage, we thought that it must be our duty to report this result. So we wrote a very simple paper. We just reported the number of muon neutrino events observed compared with the simulation. And also we did the same thing for electron neutrino events. And you can see, as you can see, at that stage already, there was a huge deficit of muon neutrino events. And we concluded that we are unable to explain the data as the result of systematic detector effects or uncertainties in the atmospheric neutrino flux. Some as yet unaccounted for physics, such as neutrino oscillations, might explain the data. Okay, that was the conclusion. But well, we mentioned neutrino oscillations, but at that stage, neutrino oscillations was just one of the possible solutions. So we didn't know what happened in atmospheric neutrinos. Anyway, already in 1988, people knew that if neutrinos have mass, neutrinos change their flavor from one flavor to the other. For example, as shown here, oscillations could occur between muon neutrinos and tau neutrinos. For example, in this figure, if a muon neutrino is produced at 0, and if they start propagating in the vacuum, then the probability of muon neutrino to remain muon neutrinos drop at some point. But if they propagate further, the probability comes back to unity. And if they propagate further, go down, go up, go down, go up. And when the muon probability goes down, at that time, tau neutrinos are appearing. So this is the neutrino oscillations, and we thought that muon neutrino deficit could be due to this effect. But anyway, back in 1988, we were the only experiment that reported the deficit. And in fact, it took us several years to get the support from the other experiment. And the support came from another large water Cherenkov detector, that was the IMB experiment. And this experiment also reported the deficit of muon neutrino events. This graph is a little bit difficult to interpret, but anyway, this tells us that there is a huge deficit of muon neutrino events compared with the expectations. Okay, at that stage, we were almost certain that there is something going on muon neutrinos. But still, we were unable to find out what was the reason for the deficit. So we really wanted to separate the neutrino oscillation possibility and other possibilities. Then we thought this way, well, of course, cosmic ray particles come into the Earth from everywhere, and therefore, neutrinos are produced everywhere in the atmosphere, and some of them are produced just above us. Well, actually, 10, 20 kilometers above us. And these neutrinos only travel 10, 20 kilometers before interacting in the underground detector. So they may have no time to oscillate. But neutrinos produced in the other side of the Earth, they typically travel 10,000 kilometers, which is a very long distance. Therefore, they may have long enough time to oscillate. Therefore, we should observe a deficit of upward-going muon neutrinos. And if this is observed, that could be the evidence for neutrino oscillations. But for this, Kamiokande 3 kiloton detector was just too small. We tried to observe this effect in Kamiokande, but, well, we worked hard for several years, but even after several years, our result was not conclusive. So we definitely needed much larger detector. That was the Super-Kamiokande detector. Okay, and of course, as many of you may know, Super-Kamiokande is a large water detector in underground. It is about 20 times larger than the previous generation Kamiokande detector. Well, as you can see, the detector itself has the diameter of about 39 meters and the height of about 42 meters. And it contains 50 kilotons of water. And with this detector, we observed about 20 times more neutrino interactions per day or per year. And by the way, this is an international collaboration. And at this moment, we have about 160 collaborators from 10 countries. And well, this is the present day experiment, but I want to tell you a little bit about the history of this experiment detector. Well, first of all, the initial idea of Super-Kamiokande was announced already in 1983. Well, this idea was announced at a workshop in KEK, Japan. And at that time, Professor Koshiba talked about this detector. And it said 32 kiloton water Cherenkov detector. But actually, the fiducial volume, which is written in this figure, is 22 kilotons. And in fact, the fiducial volume of the real Super-Kamiokande experiment is 22.5 kilotons. So, well, we stick to the initial idea for some details. Anyway, we have been working hard for the realization of the Super-Kamiokande experiment. And from the very early stage of the experiment, we started to work with the US colleagues. And this photo was taken in 1992 when we started the serious discussion between and Japanese responsibilities and the US responsibilities. And well, this was the photo after this meeting. And you can see the meeting went well because you can see a lot of beer bottles. Anyway, we started the collaboration at that point. And well, in 1995, we constructed the Super-Kamiokande experiment. And this photo was taken in the spring of 1995. And well, you can see Professor Totsuka. He was the first spokesperson of Super-Kamiokande. And also you can see a lot of people. In fact, well, in the construction of Super-Kamiokande, typically every day, these numbers of people worked in Super-Kamiokande to construct the detector. By the way, in the Kamiokande experiment, we worked on the boat. But, well, of course, we knew that the working condition was not so good. Therefore, in Super-Kamiokande, we decided to construct the detector only at the bottom. In fact, you can see above these people, there are some structures. Actually, these structures are the top of the Super-Kamiokande detector. These should be located 40 meters high. But now, that top part was located only 2 meters high. That means we had to raise the whole top part of the detector from the bottom to 40 meters. By the way, the whole structure is 300 tons. Therefore, the operation of this raising the top part is not a trivial thing. But anyway, it went well, and we moved on to the next stage. That was the construction of the side part. And again, we decided to do everything at the bottom. And in fact, we raised the tower just one by one from the bottom. Anyway, after these kind of works, we were able to fill the pure water into the Super-Kamiokande tank in 1996. And we started the experiment in April 1st, 1996. And well, in Super-Kamiokande, our target was the studies of neutrinos. Therefore, from the early days, we concentrated on neutrino analysis. But of course, the event rate observed in Super-Kamiokande is much higher than the event rate in Kamiokande. And in fact, in Kamiokande, we were unable to automate the analysis because, for example, we were unable to develop the software to identify the number of rings or ring locations. Therefore, in Kamiokande, we had to scan every neutrino event we did all kind of scanning in Kamiokande, but that was not realistic in Super-Kamiokande. Therefore, we developed a new software to identify the number of rings and identify the ring locations. Well, of course, I don't go into detail, but this development went well. Therefore, Super-Kamiokande analysis was fully automated. And these are the typical events observed in Super-Kamiokande. The left one is the typical electron neutrino event, and the right one is the typical muon neutrino event. And we observed these types of events approximately 10 events per day. And where we analyzed these data very intensively. And after 2 years of these studies, we were able to give conclusive data to the physics community. And as Hitoshi introduced, well, in '98, we still use the plastic sheet. And this is the copy of the plastic sheet we presented at the Neutrino conference. And well, so compared with the other slide, you see the difference. Everything was written by hand. Anyway, the data shown here was very important. Well, in fact, cosine theta means the neutrino direction, and 1 means neutrinos coming from above. And cosine theta minus 1 means neutrinos coming from the other side of the Earth. And you can see there is a huge deficit of muon neutrinos coming from the other side of the Earth. And also you see that this error bar is small enough, and from this data, together with some other supporting data, Super-Kamiokande concluded that the data gave evidence for neutrino oscillations. So that was the conference presentation at 1998. Now, I just want to mention a little bit about the other neutrino studies in Super-Kamiokande. Well, first of all, I want to mention that even though our announcement of the neutrino oscillation was about 20 years ago, we are still working hard to understand neutrino oscillations better. And in fact, we are improving the data from Super-Kamiokande. Well, in '98, when we presented the evidence for neutrino oscillations, the event statistics in this plot was only 531 events. But now, if we make the same plot, our event statistics is about 6,000. So we have improved the event statistics by more than factor of 10, and we are doing the detailed studies of neutrino oscillations. And I want to show you just one example. Well, already in 1998 or slightly after that, we were confident that the neutrino oscillations was between muon neutrinos and tau neutrinos. And if this interpretation was correct, we should observe the appearance of tau neutrinos. Then, well, even at that stage, we wanted to observe the evidence for tau neutrinos, tau neutrino appearance, but we knew that that is not easy. Because, well, the typical event, we expect to observe for tau neutrino interactions in Super-Kamiokande is something like this. So, well, compared with the previous event display, you can see a difference. There are a lot of rings. That is actually very difficult to analyze. So it's not possible for Super-K to identify tau events by an event-by-event basis. Therefore, Super-Kamiokande decided to do a statistical analysis, knowing that tau neutrinos are produced by oscillations. Therefore, tau neutrinos are upward going only. And this is the most updated result from Super-Kamiokande on the tau neutrino analysis. And the red part, that is the neutrinos coming from the other side of the Earth, and that red part is the tau neutrino appearance. And the data clearly favors non-zero tau appearance. And in fact, the statistical significance is well, 4.6 sigma. Well, that means we are almost sure that tau neutrinos appeared. So this kind of detailed analysis is going on in Super-Kamiokande. In addition, actually, I want to change the topic. I want to mention a little bit about the solar neutrinos. Well, solar neutrinos have been, well, the initial solar neutrino observation was already carried out about 50 years ago. And essentially from that time, we knew that the observed solar neutrinos had a deficit compared with the theoretical prediction. By the way, this photo shows the first solar neutrino experiment that observed solar neutrinos. And because of this observation, Ray Davis received the Nobel Prize in Physics in 2002. But anyway, the point was the deficit of solar neutrino was confirmed by the subsequent experiments in the 80s and 90s, but we had no clear idea what was the cause or reason for the deficit. And this problem was clearly understood by the observations of solar neutrinos by the SNOW experiment in Canada, and also Kamiokande gave some supporting data. The SNOW experiment in Canada uses 1 kiloton of heavy water, and by using the heavy water, they can measure the flux of electron neutrinos and also the flux of all neutrino flavors. And if they observe the flux of all neutrino flavors, the flux from the sun was just expected. However, if they observe the electron neutrino flux only, the flux observed was only about 1/3 of the prediction. So that means neutrinos do oscillate. Neutrinos from the sun oscillate. And in fact, well, that was the major conclusion. But in addition, Super-Kamiokande also observed the solar neutrinos, and the suggested flux was somewhere in between these two SNOW measurements, and that gave the supporting evidence for the interpretation of solar neutrino oscillations. So that way, Super-Kamiokande has been contributing to the solar neutrino oscillations. And finally, Super-Kamiokande has been contributing to the accelerator-based long baseline neutrino oscillation experiments. Well, atmospheric neutrino experiments suggested that neutrinos change their type if they propagate, say, several hundred kilometers or 1,000 kilometers like that. Therefore, the data suggested that we can have a long baseline accelerator-based long baseline neutrino experiments. And the first experiment carried out was the K2K experiment. The neutrino was produced at KEK in Tsukuba and detected in Super-Kamiokande. And this experiment confirmed neutrino oscillations with the accelerator beam. The next generation experiment is called T2K experiment. And the neutrino beam was produced at JPAC, high-intensity proton machine, and again, neutrinos are observed in Super-Kamiokande. And this experiment observed the electron neutrino appearance. That is the evidence for three-flavor oscillation effect. So that way, Super-Kamiokande has been contributing a lot to neutrino oscillation physics. Okay, well, so far, I have only talked about the data, and I only talked that neutrinos oscillate. And neutrino oscillations suggest that neutrinos have finite mass. But of course, we know that electrons have mass, quarks have mass. Why you care about the neutrino mass so much? Well, we still think that neutrino masses are important, and I'd like to convince you that neutrino masses are important. Here, I show you the masses of quarks and charged leptons. Now, I want to overlay the neutrino masses in this plot. Well, honestly speaking, we still need some assumptions, but well, forget about that. And I put the neutrino mass on this plot, and it is like that. So, well, neutrino masses are smaller than those of the quarks and charged leptons. But if you carefully read the horizontal axis, you notice that neutrino masses are much, much, much smaller than the masses of quarks and charged leptons. In fact, you can easily read that neutrino masses are approximately, or maybe more than, 10 billion times smaller than the corresponding masses of quarks and charged leptons. 10 billion, 10 orders of magnitude. Yeah, that is small. And that is the reason we believe that neutrino masses are the key to better understand elementary particles and the universe. So that is the reason we want to study neutrinos more. Now, finally, I want to talk about future neutrino oscillation experiments. As I said, we knew that neutrino masses are extremely small, and we think that this is the key to better understand particles and the universe. So we want to get as much information as possible from neutrinos. And well, in fact, today I only talked about the Super-Kamiokande experiment, but in fact, in the last 20 years, there were many experiments that contributed to our understanding of neutrino masses and mixing angles. And now we understand neutrino masses and mixing parameters quite well. And we think that we understand the basic structure for three-flavor oscillations. Okay, that is the status, but there are still some unknowns. First, I said that, well, I showed in my mass plot that the third neutrino masses are the heaviest, but actually we do not know. Maybe the third neutrino mass state could be the lightest. We do not know, so we have to check. Also, we do not know if the oscillations of neutrinos and oscillations of antineutrinos are identical. Actually, this is a very important question because we believe that maybe neutrino masses are related to the baryons of our universe, baryon asymmetry of the universe. And finally, there are several more questions. We do not know the absolute masses of neutrinos. We do not know if there are, say, some other neutrino flavors. And finally, we do not know if neutrinos are special particles. Well, we say Majorana particles. That means basically neutrinos and antineutrinos are fundamentally same. But anyway, For this talk, I want to concentrate on these two topics. And these two topics are studied by neutrino oscillation experiments. First of all, I want to talk about the neutrino mass hierarchy. That means we'd like to know if the third neutrino mass state is the heaviest or the lightest. And for this problem, there are several proposals or projects going on. So this is the list of the projects that try to determine the neutrino mass hierarchy. First of all, I think it's healthy that we have this many experiments proposed or going on. And we think that we know the neutrino mass state is the heaviest or the lightest, definitely before 2030. And in addition, we have another problem. We'd like to know if the oscillations of neutrinos and oscillations of antineutrinos are identical. Well, of course, we'd like to check this with the experiment. But unfortunately, this is not an easy experiment. So we need the next generation long baseline experiments with much higher performance neutrino detectors. And for this, we have two proposals, one in United States and one located in United States, one located in Japan. And well, in the next page, I want to talk about a little bit about the next generation neutrino experiment that is proposed in Japan. Well, we think for the next generation experiment, Super-Kamiokande 50 kiloton detector is too small. So we wanted to have a larger detector with the higher performance photo detection. So in fact, people are thinking about the 74-meter diameter and 60-meter high water tank detector. And well, the design report has been finished. And this detector is, in fact, very useful to study neutrino oscillations based on accelerator beam, atmospheric neutrinos, and solar neutrinos. And we definitely want to observe proton decays. We have been searching for proton decays for 30, 40 years. And we'd like to observe supernova neutrino burst. We saw only once 30 years ago, and we want to observe the second one, and past supernova neutrinos, and so on. So we have a lot of physics with this detector. And well, I want to tell you a little bit about the status. This experiment has been selected as one of the 7 large scientific projects in the roadmap of the Japanese Ministry of Education, Culture, Sports, Science, and Technology. And well, that's great. Well, we were selected, and we are just waiting for the project approval. And we'd like to work hard for the construction of the Super-Kamiokande experiment. Okay, let me summarize. Proton decay experiments in the 80s observed many contained atmospheric neutrino events and discovered the atmospheric neutrino deficit. In 1998, Super-Kamiokande discovered neutrino oscillations, which shows that neutrinos have mass. And Super-Kamiokande contributed to the studies of solar neutrino oscillations and to long baseline neutrino oscillation experiments. The discovery of non-zero neutrino masses opened a window to study physics beyond the standard model of particle physics. And we think that the studies of neutrinos are extremely important, and there are still many things to be observed in neutrinos. So I think we still have to work hard. That's all. Thank you very much.
So now you have seen how nice person he is, right? And so he made this major discovery based on the failure to observe the proton decay. And for the mistake of writing a software, that turned out to be a major discovery. So that's really an amazing story. And in this world, 50,000 tons is not big enough, apparently. So there's a lot to look forward to. So now we can take some questions from the audience. So please raise your hand, and please try to be very brief when you ask questions. Okay, back there. And please stand there, wait for the microphone. And especially encourage questions from young students. Yes, please.
The electron neutrino is made mostly of the light neutrino.
Can you point the microphone better?
Closer.
Is it turned off?
Oh, it's turned off?
Oh, okay. Electron neutrino is made primarily of the light neutrino with admixtures of medium and heavy neutrinos, and the mu and tau are also constructed of those three. Because the electron neutrino has a certain amount of heavy and medium neutrinos in it, it has mass. Is it known yet whether the light neutrino all by itself has mass?
Oh, you are talking about the mass of the lightest neutrino state.
Not the lightest observable neutrino, but the eigenstate of the neutrino.
Mass eigenstate.
Yeah.
Yeah, actually, we do not know if the smallest mass eigenstate has the finite mass. We do not know.
Okay, next question. Further back?
Further back.
Yeah. Oh, okay, the way back then. Stand up. Can you stand up?
When you mentioned that you couldn't identify a single tau event, but that you could do the statistical analysis, given that you can't tag the single event, how can you actually, and it has so many rings like that simulated image for the tau event that you showed, how can you actually tell that one of those is upward going versus downward going for the statistical analysis?
I see. Certainly, for that particular event, it may not be so easy to tell you the direction of the neutrino. However, well, according to our analysis, even with that kind of event, we can say take the momentum sum, and with that, we can reasonably reconstruct the neutrino direction.
Thank you.
Okay, stand up. Wait for the microphone.
Hi, thanks for the talk. So it sounds like the data you're collecting depends on neutrinos passing through your detector. And you'd think naively that the size of your detector just increases how many neutrinos you'll get passing through it per unit of time. But you made it sound like these bigger detectors are required for some of the things you're trying to show. So could you explain why it's why you need a larger detector and you can't just wait longer with a smaller detector? You know what I mean?
Yes. We can wait longer with the small detector Super-Kamiokande. Yes, that's true. But well, if the hyper-Kamiokande is in operation, the fiducial mass is about 10 times larger. Therefore, you can finish your experiment in 10 years rather than 100 years.
Especially when you have a PhD degree, right? More questions over there. Please stand up and wait for the microphone. In the third row.
Since already the Super-Kamiokande has been approved, I wonder why, instead of going in that direction of increasing the volume of the detector, was not, for example, change the going into heavier, like did Canada with heavy water, or maybe using another noble gas that could have been, didn't require the huge size.
I see. Well, okay, that is, using different material is certainly a possibility. However, well, of course, if every experiment needs the budget for constructing the experiment detector, very fortunately, water is cheap. So we want to use water still.
Very convincing. Any more questions? Up front, Doug? Oh, the first row.
Yep. Since we don't know the masses of the neutrinos exactly, what kind of experiment or what kinds of experiments are being proposed to actually try to measure that at an absolute,
I see.
absolute way?
Yeah. Okay, thank you. Well, there could be several ways. One of the trivial ways, experimentally, that is not trivial at all, but is to measure the spectrum of the electron from the beta decay. If you have the very precise measurement, you get the effect of the neutrino mass. But unfortunately, in reality, even if you have a huge detector, you may not have enough sensitivity to tell the absolute neutrino mass. Then other ways is to have the very precise measurement of the universe. Depending on the neutrino mass, various distributions are different. So if you have the very precise measurement of the universe, you get the information of the neutrino mass. And finally, if you have the special, if you measure the special beta decay, we call neutrinoless double beta decay, that would tell us the neutrino mass.
And a lot of people in the department are working on that experiment. Second row, stand up.
Thank you. Are there other particles that oscillate in the same way that the neutrino does?
That I don't know. Maybe kaons? Kaons? Yeah. But kaons are K0, K0 bar.
But for different flavor too, right? Strange is plus minus one.
Okay, so that means kaons. Okay, thank you very much.
Okay, back there. Please stand up.
I just wanted to make a historical comment and then a question. I wanted to point out that one of the people you showed up there on the solar neutrino experiment, the first one, was John Bacall. John Bacall lived in this house when he was an undergraduate student here.
Oh, I see.
So that's something that you can always say that you started in a good place, especially if you lived here. Yeah, he and I used to play tennis down on the Bancroft courts way back when. And of course, he went on to great things. My question is, if the neutrinos have mass, they can have various speeds. They don't have to go at the speed of light. I've never heard of an experiment that detected as neutrinos going slower than about the speed of light. Why is that, please?
Oh, I see. Okay, well, although the neutrino speed is slightly slower than the speed of the light, but the difference is so small. Therefore, in reality, it would be extremely difficult to observe this effect. For example, yes, slower than the speed of light. But, yeah, well, for example, 30 years ago, Kamiokande and IMB observed neutrinos from this supernova. And these neutrinos propagate 160,000 years, but the expected time delay was unobserved.
Where were the slow ones?
Huh?
Where were the slow ones?
Slow ones? Slow ones?
I don't know. Just to put them in perspectives, for those neutrinos, they traveled 160,000 years, and they came within about 10 seconds. So difference is so small.
No, but why weren't some slow neutrinos produced so that they could dribble in? Some arrive quickly and some arrive slowly.
Basically, there are very few of those produced by supernova explosions. Very few of those produced by supernova explosions. Most of them just blasted out. Okay, more question over there? Oh. Yes? Third row. Stand up, wait for the microphone.
Hi. how does the mass of the neutrino correlate with or does it correlate with the oscillation? And could you measure the mass from the oscillation?
Okay, yes. Oscillation length is a function of the neutrino mass difference. So we get the information on the neutrino mass, but not exactly the absolute mass. Difference.
Yeah, you can constrain the range by difference of masses, but not absolute masses. That's why he said. Okay. Any more questions from the audience? And way back, the last row. Stand up, please. Well, wait for the microphone.
Thank you very much. So, your Nobel Prize, what did you discover? What report did you make that gave you a Nobel Prize, and what year was that?
You mean the year of Nobel Prize?
No, you have to do something. What did you find that they wanted to give you the prize for?
Well, he did a major discovery that neutrinos oscillate.
What year was that?
98年って言っていいですか? はっきり
Yeah.
1998.
Okay.
Are you happy? Okay, in the middle here. Stand up.
Thank you, Professor. We know that there is a dream in modern physics about the unification of physical theories. So I want to ask that your discovery and concerning neutrino physics, to what extent will this discovery lead to the, for example, the grand unification of particle physics? Thank you.
Well, okay, maybe this question can be better answered by Hitoshi, but anyway, let me say the introduction of the answer. Well, okay, we think that, neutrino masses are really too small to be understood within the standard model. And we think that in order to explain the extremely small neutrino mass, we need another mass scale, and that could be related to the grand unification. In that sense, neutrino masses could be an important input to the understanding of the grand unified physics of the grand unification.
And that is the answer to your question. So that's perfect. Any more questions? There? Stand up, please.
Hey, Professor, thank you. So actually, I just came from an undergraduate lab course, which the chair of physics department just introduced. And in our lab, in our very small experiment, we had some noise that affects our results. So I'm wondering, like, how did you lower the noise in your experiment? And for example, there are similar particles that can interact with the detector in similar ways. So how do you lower the noise other than putting the experiment underground?
How to lower the noise? Well, okay. Well, basically, simply as an experimentalist, we do everything we can do.
That's a good answer, too. Maybe the last question now. Any last question? Okay, up there.
Hello. Hello? You worked many years on Super-Kamiokande and Kamiokande, very delicate experiment. Did you have anything that broke while you were working? Did anything break while you were working on the experiment?
Well, okay, I'm not sure if I'm not sure about your question, but yes, after say 30 years, I started to think something else. So now, actually, I'm working on gravitational waves now.
Okay, I think that was a very good answer to your last question. And if you think that you haven't gotten enough of Professor Kajita today, you're not alone, and you have another opportunity to listen to him again tomorrow from 3:30 in the same auditorium right here. And that's part of the symposium called Drive for the Nobel Prize. And we have 2 more Nobel laureates speaking tomorrow. Two of them are Berkeley Nobel laureates. One of them is Yuan T. Lee, the chemist, and Saul Perlmutter, physicist. And whole symposium starts at 9:30 in this building and goes on tomorrow and a day after tomorrow. And there's many interesting talks coming from the media, government circles, and also the current member of Nobel Committee will be speaking about selection process, how he was chosen to receive Nobel Prize. Not quite about his case, but some past cases he can disclose apparently. So that I believe is also very interesting. If you just Google up Drive for the Nobel Prize, you can find more information about this symposium. So let us just give him a round of applause about this wonderful talk he has given us today.
Thank you. どうもありがとうございます。